we left off talking about density, and pretty much that's the only real formula you're going to have on the test, or have to know on the test. So the next little part, we're running through just some filler kind of things. I run through it pretty quickly because honestly it's some stuff that is basic knowledge at this point. You've seen the metric system. I just quickly review some of this stuff. I am going to give you some papers, but that's more for if you need to practice. Honestly, if you can look at some of this and you already get it, that's fantastic. But if I give you a sheet of paper, the reason that has some practice on it, if you think you got it, you don't have to do it. But if you need the practice, then I would do it. But you know. Anyway, so units. We already talked about units already. It's very, very important in this class. There's rarely any time that you're not going to use a unit. Very rarely. Or some things will not have a unit. But I will specifically tell you when they are. Until then, assume everything has a unit, and always assume to at least round to, a couple decimal places. So units. Units tell us two things: the type of measurement and the magnitude of it. You'll notice that if we just say meters, that's just a type of measurement. If I say kilometers or millimeters or centimeters, that's the magnitude of the measurement. In other words, there's different degrees. So for example, 32 seconds, that we know it's a unit of time, and the magnitude is very small. What's bigger than seconds? What's bigger than minutes? What's bigger than hours? What's bigger than days? Well, weeks. What's bigger than weeks? Months. What's bigger than months? Years. What's bigger than years? Decades. Okay, you see how it gets bigger and bigger? We could get smaller than seconds. We can get really, really small, which is milliseconds and things like that. So anyway, examples. Another example here is 32 tons. That is a large magnitude, but you know that that's a type of weight. Another example is just basic meters. 32 meters. It's a medium. It's actually right in the middle. That is what we call a base unit, is meters. If I say kilometers, those are bigger than meters. So that magnitude would be larger. If I say millimeters, we know that's really, really small. So that'd be a smaller type of measurement. But anyway, we mainly use, in this class, we don't really play with time very much. You will in physics. But in here, we mainly deal in grams, liters, and meters. So we like to cover the distance, the volume, and the weight, or I'm sorry, the mass. So anyway, we use the metric system, and the metric system is based on units of 10. Now, I'm not going to preach to you about how the metric system is better because, well, the rest of the world uses it. But one reason why we kind of don't change is because, well, why do you think we don't change our system? And don't say tradition. It's not tradition. We want to be different. That's the other thing. Nope, not because we want to be different. Think more like a politician. One is change, but what else?
So the mass of the population doesn't know it.
Mass of the population doesn't know it. Well, they could learn it. The biggest issue why we don't change the metric system, because we've thought about doing it, how much would it cost to change every single mile marker to kilometers? Lots of money. So that's one example. Also change everything that we currently make to that kind of system. It would cost too much money. And let's be honest, nobody, it's not a life or death situation. So they're not really caring. I got you 10 roses because I believe the relationship should be based on the metric system. So the metric system is based on units of 10. Why 10? And if you already know it, don't say it. How many fingers do you have? 10. That's why. 10. Why do we score people up to a 10 in Olympics? It's very important that you know that. It is the number 10. We count things by 10. It's a lot easier to move the decimal place than actually try to convert things to different numbers. Why is it 12 inches in a foot? That was just because the king at that time had 12 inches in a foot. Or that's how long his foot was. Another reason why structures are screwed up over there. Every time a new king came in, whoever the king was at the time, that was a foot. They used his foot. That's why we would measure things in feet. Anyway, so that's basically one reason why. So we use meters, grams, and liters, and you're going to see that a lot in this class. English system, which is really based on like Old English, is mainly used only by Americans. I mean, other places in the world do use it a little bit, but mainly they deal in the metric system. The metric system, believe it or not, is actually easier. The only reason why it's kind of complicated for y'all right now is because traditionally you've been brought up to deal with feet, pounds, fluid ounces, and things like that. If you were raised in that way, you'd be like, oh, well, that makes sense. For example, Celsius, it's a lot easier to get temperature in Celsius. And we'll talk about what all those temperatures are based on way later when we get to the gas laws and things like that. Okay? So there is no fault in the English system, but it does have to deal with, you know, a little bit more measurement, a little bit more math. In the metric system, all you got to do is just move the decimal. That's it. We'll do some examples here. So, you probably have seen this. What was it? Y'all probably remembered some silly acronym like King Henry died doing something. I don't know. So, anyway, basically, this gives you an idea of which way to go. I'm going to go ahead and tell you in this class, we don't really use deci. We don't really use deca. We don't really use hecto. We will use kilo, centi, and milli. Only reason why we use centi is because, well, most rulers have centimeters written on it. We use milli for mainly because of milliliters, kilo mainly because of kilograms. And so base unit could be any of those units that we in the middle. So for example, like meters, grams, and liters, that's the base unit. That's the middle part right there, the creamy filling. If we wanted to move the decimal to the left, we'll actually make things a little bit larger. Now notice when they say kilo, that's not saying 1,000 kilo is equal to, you know, 1 base unit. It's actually the other way around. In other words, if I have 1 kilogram, I have how many grams? Nope. 1,000. That's what it actually means. So for example, if you're looking at the stair thing, I'm going to give you a sheet here in a second. So if you have 5 grams, how many kilograms is that? Well, you take the decimal, 1, 2, 3. Why 3? 1, 2, 3. So really, if you're converting this to kilograms, it'd be 0.05 kilograms. And typically, that's what the main idea of the whole stair-step method is. However, in this class, you do need to know its actual equal value. However, when they teach you doing the whole stair-step ladder kind of thing, actually, it's just like that little pyramid thing I showed y'all earlier. To me, that's a handicap. You're actually still having your training wheels on. You need to take those off and be able to ride the bike like a big boy and girl. So, you mainly need to know what is equal to what. If I do 1 meter, I said, how many centimeters is that? It's the same difference. It's just a different unit. So, obviously, you know centi means what? 100. If you didn't know that, you better be practicing. Milli means one more over, or millennium. We're not going to use deci, we're not going to use deca or hecto. So do not worry about those guys. We do not use them in here. We just never have practice with it. But you do need to know some of the basics. For example, if I'm just going to use meters since we're all familiar with distance by now. That 1 kilometer equals 1,000 meters. That's one of the typical ones a lot of people need to know. If I said I have 1 meter is equal to 100 centimeters. So, and also if I say 1 meter, how many millimeters is that? 10,000? 10,000? 1,000. So some of those are like the typical kind of setup right there, and actually that's the kind of the ratios that you need to know. Everything in this whole little thing that we're going to end up doing is going to be based on ratios. All right. So another thing that should be kind of second nature is how to figure out a percent problem. And so it's probably been a long time too, so that's why I'm doing this refresher. So percent. The formula for percent is always going to be part of a whole times 100. That's how I figure out your grade. So it's how many you get right out of the grand total. And that's how you get your percent. Actually, your grade, if it's a 98 versus an 88, that's a percent. We take all those percents, put them together. And that's how we figure out like how much, you learn. It's the only system that we pretty much got right now. It's been around for a while. Anyway, so for example, if you ate 3 eggs for breakfast out of a dozen, how many eggs are in a dozen?
12.
Yay. Glad y'all knew that. So if you ate 3 out of 12, what % of eggs did you eat? Now think, they said, did you eat? So if you ate 3 out of 12, 25%. And y'all could have figured that out actually in your head, because if you reduce this, that's going to be what? 1/4. And you already know that's a quarter. I was about to put a cent sign up there instead of 25%. All right, so that's that one. Now they also ask you this. What % remains in the cart? And 2 ways you can figure this out. You can subtract 3 from 12, put it on top, which would be 9 out of 12, and that would give you the %. Or, since you already figured out 1/2 of the whole thing, what could you subtract it from? 100. And so what's left in there is 75%. So there's many different ways you can actually do it. Either way, you can check your answers to get it figured out. But typically, you should be very familiar with percentages. Now, here's where it gets a little crazy. These problems, like, yeah, I could do that. All right, well, let's kick it up a little bit. Okay, what if I give you the %, and then you got to go back and figure out how many you had to get, or let's say I give you a test that was out of 10 questions, and you want to ask me, like, how many points do I have to get just to pass pass? And I was like, well, if a passing grade is 65, you need to then figure out of 10 problems how many you can miss. So you have 45 people that work at Walgreens. Okay, so total, right? So grand total, 45 people. That's a lot. So the whole % of them right here, 35.6% of them work part-time. How many employees are full-time then? Well, here's the thing. A lot of people automatically start putting everything into here. They're like, okay, I got to find this, and I have 100. Oops, sorry, time's right here. 100, and that's a %, so I'm just going to plug that in, right? Okay, what's the problem with this right off the bat? If you solve for X, that's not going to give you the employees that are full-time. Why? Read closely. This percentage is associated with part-time. So that's the problem. A lot of people immediately just start plugging things in. And that's, you got to read a little bit, okay? So you could plug this in, get that value, and then subtract it from the total to get the other guys. But there's an easier way if you just want to go ahead and solve for X right off the bat. Again, all percents add up to, so what's 35.6 minus 100?
64.
You did it on top of your head? Okay. Thanks for being awesome. All right. What'd you say?
64.4.
0.4? Okay. That's better. So we want to use that right here. Okay. Then you put it in, you solve, do all that kind of stuff, and then what is your X going to be? Yes, you must find your X. It's not stalking if you're finding your X. It's all right. In math, it's all right. In real life, it's probably illegal. 28.98. Well, there's a problem there. Can you have a 0.98 person? Like somebody might be missing a pinky. So actually, what is this one?
29.
20. We got a round. 29. So 29 people are actually employed then full-time. Then how many are actually then employed part-time? They don't have that question up there, but I'm asking you. How would you figure it out? 29 from 45, which is 17? 16. 16? 16. Y'all concur? Anybody want to debate him? No, that's right. Isn't that right?
Yes.
That's right. Okay. I swear I thought it was 17. It's been a while since I've done this one. Okay, so percent problems you'll see. Don't worry, I'm going to give you a practice sheet with that too to help practice in case you've been a little foggy for percentages. And it's a good practice. You don't want to get the test and have anxiety and then like, I didn't practice. So anyway, percent versus accuracy. This one's actually not so bad. This is more of a visual thing than anything else. So we got to look at some of the definitions. And I'm going to give you the definitions real quick before we actually start doing some examples. Some of y'all can look at these bullseyes right now and tell me who is the better archer out of all the rest. The one on the top left. But the one on the right, top right, isn't so bad either. If you average all his shots together, he'd be hitting the bullseye. So if I was sighting in my gun for hunting season, which I do every year, just to make sure I'm still hitting the bullseye. So if I actually was shooting a target, and usually I'd shoot about 3 times, sometimes 5 just for fun. But if I was hitting this, I was hitting the middle target about this much, I would say my gun's sighted in. Good, I don't have to adjust anything. But even if I was kind of doing this, I'm still killing the deer. It's still, if I average them together, that's still a kill shot. I might be hitting around the heart, but I'm hitting the deer. It might not be a bullseye, but I'll get them. Okay? The 2 at the bottom, though, not really so much. If you average these shots together, I am missing the kill shot, so I might just injure them. This one, definitely way off. If I'm aiming at the bullseye and I'm hitting down here, there's something off. I'm getting a gut shot or the shoulder. So looking at the one at the top left, that's the best one. And when people get these 2 terms mixed up, precise and accuracy, okay? Would you say this guy's very accurate? Yeah. Would you say he's being pretty precise? Yeah. Both precise and accurate, okay? So really, this is where we start trying to figure out our definitions, okay? What do these guys actually mean? So I'm going to actually show you some pictures and give you actually what's happening, and then you try to come up with your own definition. That's what I do, and that's how I actually learn stuff. So that first one is both accurate and precise. All right, he's hitting the goal, and he's kind of doing it more than once. So you start getting an idea of what these words actually mean. Whee! Say, okay, so the one onto the upper right, all right, he is not technically touching the bullseye all the time, okay? But, he's not repeating in the same place, but we did already say if it averages together, he's kind of hitting the center, right? Well, like some of y'all, you might not get the full 100% on the test, but you'll, get up there pretty high. It's not bad. So this guy is actually going to be accurate because if you average them together, you're going to hit the middle. But he's not very precise. He's not repeating himself, okay? That's just like y'all taking 3 tests. You make 100 on one, and 85 on another, and a 60 on another. Oh, I'm not a 60. That's actually pretty bad. Let's say 100, 95, 90. On average, you're going to have, that's a 95 average. So that's actually good, but it's not really precise. You're not really repeating in the same location as often. Whee! Okay, bottom left. We already said. So now, do y'all think he is accurate at the bottom left? No? Okay. Is he precise? Yes. So this is what's crazy. He's precise, but he's not accurate. He's repeating in the same place, okay? But he's not hitting the goal. That's a lot like some people getting a 70, a 71, and a 72 on a test. They're repeating themselves, but they're not hitting the goal. The goal is 100%. You want to be both accurate and precise. That's the ultimate goal. Mostly you want to be accurate. Whee! Last but not least, this guy, bottom right. Neither. He is not repeating in the same location. He's not doing that at all. He's all over the place. He's also not hitting the goal at all. So he's neither accurate nor precise. Okay, so now the definitions, as we already kind of gave out to you a little bit. Precision is consistency in data. When you go in the lab, if you were to redo the density lab that you did yesterday over and over and over again, you did it once, okay? Which obviously that's not, obviously in lab you want to try to do it at least 3 times, but who's got time for that? But if you did do it over and over again, you might get a different number every time with the same stuff. But the reason why we do that is to find out our accuracy. 3 trials of an experiment showed that density of aluminum, and y'all did, not aluminum, y'all did zinc yesterday, which actually the density of that is 7.14. If you got around 7.14 as your density, you were very close to the goal. Okay, some people got 1, and it's probably because you use smaller pieces of the zinc, and that's not really a bad thing. As long as you got above 1, that's actually good on your measurements. But some people got around 6 and 5 and things like that. But you were still kind of off by a certain percent. But anyway, if you were to do it again, though, you should get some range of numbers that you see right here. Let's take a look at this person's. They got 4.45, 4.48, and 4.47. Is that, are they repeating? Well, are the numbers close together? Yes, okay. So they're not repeating the same number over and over, but they are getting a very close number, 4.4, 4.4, 4.4. That's very good. I would look at that if a student was getting that. I'm like, well, it looks like you're very consistent with your data. However, the goal was this. Are they very accurate, though? No. The 2.7, they're off by, it looks like 50%, okay? And that's typical, you know, when you first start out. That just means there's probably something wrong with the technique. So you can see like how we have to try to figure out things in science. It's not really, it is kind of cut and dry, but it's not the kind of cut and dry you want. So looking at this socrative, this is the last one. It really should say, you know, unit 1, quiz 4 or something like that, or lecture quiz 4. The other, I forgot to, you know, I just didn't copy it right. Anyway, so number 1 says up here, the following picture is, and this is the picture right here, they are repeating in the same place, but are they hitting the goal? No. So they are not accurate, okay, but they are precise. So we find the one that's C. Okay, so they are repeating, but they're not hitting the goal. So that's kind of how you could see some of these questions. Now I could just replace this with a real gun and actually blow holes through it, but obviously it'd be a little bit, wouldn't be this bad of a picture. It'd actually be kind of in color. Number 2, the blank system is based on powers of 10. That would be the metric. The English system is what we currently use in America, which is not based on 10. It's based on everything else. Number 3, you get 15 out of 25 questions correct on your lab quiz. What percent did you get correct? So you got 15 correct. Okay, you got that right. Okay, that's not saying how many you missed. You got 15 out of 25 times 100. That's going to give you your percent, which is 60. Did you pass? No, you failed. You try harder. Okay, number 4. You have consistency to have consistency in that. I don't know why it said date. It should say data. Okay. Yeah, that was weird. I don't know why it's. I guess predictive text. What are you gonna do? To have consistency in data is what? It'd be precision. It's all about the repeating. Okay. Dimensional analysis, and you're going to get a little something like this. You're not getting this sheet, but this is some samples I'm going to work out. So yes, you do need to write this down. I'm only worried about on the test mainly the setup, not the math. Okay, let me repeat that again. I'm worried about the setup, not the math. Okay, the math will come later, trust me. But I would rather get you in the rhythm of trying to figure out how to set things up. You need to know this right here. I actually like how this person did this one. Don't forget how to start doing the conversions. It's what you got on bottom and then what you want to go to on top. This is very important. If you're planning to go to med school or be a nurse or something like that, there's a class called dosage you have to take. It is nothing but conversions. And people fail it because they don't know how to do dimensional analysis. And it's so easy. It is so easy. They just got to do this and think a little bit. Let me start with this right up here. I'm going to make up a sample problem just to kind of, because I don't like the first one that they started out with. I have, let's see, I am 74 inches tall. I want to know how many feet that is. So in dimensional analysis, anytime you're in a math class, if you have a whole number, but I want to put this in fraction form, what usually goes on bottom? What's usually invisible here?
0.
Not a 0, but a 1. Okay? So anytime you have a whole number, like right here, that's 5,400 over 1. This right here, 16 weeks. That's 16 over 1. That's one thing to kind of think of, okay? That 1 has no unit. It's just what we put on bottom, okay? So all this is nothing but ratios. I'm trying to go to, I want to go from inches to feet, okay? So the question then is, what's my ratio between inches to feet? How many inches are in a foot? In 1 foot, there are how many inches? 12. Okay? So I don't want to know the final answer. I do, but to get there, I'm more worried about this little setup that you need to have right here. My thing is, I want to know what goes right here, because I'll go ahead and tell you what the final answer is. It's going to be 6'2", but I'll get to 6 foot 2 inches, but you're going to get a decimal in feet. But anyway, I'm worried about the setup right here. There's a fraction you got to put here within a ratio. So anytime you see an equal sign like this, it can be represented as 12 inches are in 1 foot, or 1 foot, 12 inches. That's what it means. I don't know if you ever noticed this. When we write an equal sign, it's a fraction. Mind blown. Yes. So here's the thing. This either goes here or this goes here to find the answer. So you got to figure out or tell me which one has to go in place of that little box. So I'll tell you a trick to figure it out. Don't you know whenever you do fractions, like terms cancel out if they're crisscross from each other? So which one of these would have to go on bottom to cancel out the inches? The 1 foot over 12 inches. Because what happens there, that's how you know how to put things anywhere. It's usually going to be from top to bottom. You're trying to figure out what to cancel out. I'm sorry, I put F. I should have put a T there. So the answer really would be, if I asked this on a test, you'd have this blank and I'd give you the answer over here. Real quick, what is 74 divided by 12? 6.17? Okay, so that'd be 6.17 feet. I'll even have the answer there. I'm more worried about the setup, because that's dimensional analysis. And there'll be some practice on that little soccer I'm going to give you later tonight, which mainly has to deal with knowing which one goes where. Okay? So all this is working on the setup. I mean, you could go ahead and find the answer, and I will have the answer for each one. But this little setup is the thing that I am really, really worried about, is knowing which one goes where. Now, if you're ever confused, just always ask yourself, what has to go on bottom to cancel this out? If you put this guy on bottom right here, you'd have inches across and then feet on bottom. You'd end up with your answer being in the units of feet squared over inches. And that's just silly. Nothing in the world is used to measure it in that. That's not useful for anything. You don't want that. So you got to kind of think mathematically, how do I cancel this guy out? Crisscross. Now, you'll see me later end up doing something called the train track method, where I put things up here and I move through. It's the same little thing that we're going to end up doing. But I'd rather y'all kind of get practice with this in the setup. And that's really all there is left for the test. I'll do some quick little practice things right here real fast. So if I got 5,400 inches over 1, I need to figure out some ratios to get to the end here. Okay? So here's the problem. And I will tell you this, okay, just so you don't freak out, all right? Common things I do expect you to know. Obviously, 12 inches in a foot, 3 feet are in a yard. I don't expect you to know that there's 946 milliliters in a quart, okay? I don't expect you to know there's this many grams in a pound off the top of your head. Those are just not very common right now. So I would have to give you some things up here in a ratio, so don't freak out. If you're like, oh, I don't know how many, centimeters are an inch. That's going to come later. But, so I'll have to give you some of these kind of things. All right, so we're trying to go 2 miles. There is no quick how many inches are in a mile. All right, so you're going to have to do more than one step. So think, what's in between inches and miles? Feet. There is a connection here. There is a feet here, and I think, did they have feet somewhere else? 3 feet to 1 yard, but that's, yeah. So what we need to do is figure out, first off, we got to convert our inches into feet, and we kind of just did that up here. So let's do it again. First off, we know that we're going to use one of these two little ratios. All right? Which one has to go on bottom to cancel out the inches? Inches. Why inches on bottom? So they cancel. And guys, that's really the whole hard part about dosage. It's really just trying to figure out, oh, well, you got to put this on bottom to cancel out. Now you're in feet. Usually we save the math till the end. Like you put it all in at once and you're done. But you're not done here. You're in feet. You got to get to miles. Okay? Well, now we need another ratio. Luckily, they gave you that up here. There are 5,280 feet in 1 mile. So you're either going to have this guy on bottom and this guy on top, or this guy on bottom and this guy on top. Well, how do we know which one goes on bottom? The one you're trying to cancel out. You have feet right here, so what has to go here? Feet. And then if the feet went on bottom, that mile's got to go on top. Feet's done. Now how this would look in your calculator, okay? Well, obviously, if you know you're going to take the top multiplied together, this times 1 is going to be the 5,400. This is just a little extra stuff. I'm more worried about this on the test, okay? So 5,400, and then you got 12 times whatever that is. That's how it would look in your calculator. I do not have a calculator in front of me, but y'all do. What was it?
63,360. No, like under 5,400.
Oh, you did the bottom thing. Oh, okay. Well, what's the grand thing? This divided by this times that. I usually put it all in my calculator at once and it gives me the answer. It's a lot easier. You can do it in steps. 0.09 miles. That's actually very easy to run, if you think about it. So again, how this would kind of look on a test, I wouldn't even have this right here. I would have probably a blank right here, or a blank right here, and then the final answer. So what I would want to know is what would need to go on top and bottom to actually cancel it out. So I can ask that in many different ways in a multiple choice kind of setup. It's very important that you kind of look and you kind of know. We'll do one more sample, okay? All right, this one is a little mean, okay? So we talked about time earlier. We're going to get to seconds. So we have 16 weeks, and we need to get to seconds. Okay? Well, there's no one conversion from week to seconds unless you're Rain Man. So we got to get a little bit smaller every time. So if going from weeks, what's our next little small thing we can go to? Days. In 1 week, how many days? 7 days, typically. 7 days. Sorry. So now we're in days. Weeks have canceled out. All right. We got to get to days to seconds. So what's smaller than a day? Hours. How many hours?
24.
Or 1 day. Okay. So far, so good. So now we're actually getting into a clock now. All right. So now we're trying to get to seconds still. So what's smaller than an hour? Minutes. How many minutes are in an hour? 1 hour, there are 60 minutes. And you'll notice that we're still kind of using this little trend up here. Oh, sorry, not just HR. Hours have canceled out. Oh God, when will it ever end? Well, it's about to. So now we're about to go from minutes to seconds. How many minutes are there in a second? Wait, how many seconds are there in a minute? Sorry. There are, in 1 minute, 60 seconds. So I'm more worried about the whole setup than anything else. Now, yes, if you put this in your calculator, you could take 16 times 7 times 24 times 60 times 60, and that actually will give you your answer because everything on the bottom here is 1 times 1 times 1 times 1 times 1. So I'll go ahead and tell you, you're going to end up with a big number here. big number. So actually tell me what the whole number is, because there is something else we got to do here. Okay, so just tell me the number in order. Let's do it that way. 9, 6, 800, 0?
No, 800.
800. Okay, that's good. All right, so that's how many seconds, and you can actually figure out how many seconds you've been on the planet. It's actually kind of weird when you do it. You're like, oh, that's it. It's like crap. So anyway, so 9 million, and all that crap. Anyway, that's a lot to say, right? Well, in science, we do things a little bit different. We're going to put this in scientific notation because that's a big number, okay? We're going to still keep it in seconds, but we want to move that decimal so we don't have to write all this, but yet still get the same kind of value, okay? So typically, when we do scientific notation, we want to move the decimal but keep the same value. So when we do this, 1, 2, 3, 4, 5, 6. 6 times to the left, okay? So when we do that, we get 9.6, and we round right here, just to be safe, times 10 to the 6th power, or to the negative 6? Is it negative? It is positive. I was messing with y'all. Yeah, I did. So how to check this? Okay. By the way, how I would do this, I was so paranoid when I would do scientific notation. I would put this back in my calculator. And now if you have your calculator set to scientific notation, it's automatically going to put it in this form. And then I think you go to mode. Can I see your calculator for a second? I think you can do it on this. You go to second DRG, and then you go from flow to psi. And it would automatically put it in there for you. However, you just need to remember to go back, because some people get annoyed with that. I will tell you, if you put anything in scientific notation, you're probably going to get it right on the test, because scientific notation is the great way to round and get a good number, and it does it for you. So you can go ahead and put your calculator in scientific notation. Again, on your calculator, it is a DRG. Well, you got to hit second, then DRG, and then go over to, that's a G, not a 6. Then you go over to psi. If you want to go back, you go back to flow, and it'll do that. But it's really up to you. If you're just paranoid, just leave it in psi. But I will tell you, put every answer in this little form. Scientific notation basically takes every decimal, puts one whole number in the front, but yet keeps all the numerical value. This number still equals this. It's just been rounded. Okay? So you probably ask, like, why 2 decimal places? Am I going to say, well, typically if you put scientific notation, it's going to do it for you. And you don't have to write so much. And you'll see and it's just easier to get used to this guy right here. If you do put in scientific notation, do not put down your answer as this on the test. That is not the same as that. You're missing out on this. This is like 6 decimal places. That's really bad.